Hello everyone. Welcome to the presentation of the paper An Ontology for the Materials Design Domain in Resource Track. My name is Huanyu Li, a PhD student from Linköping University in Sweden. This is joint work with my supervisors, Professors Richard Armento and Patrick Lambrix. In this paper, we present the Materials Design Ontology, MDO version 1.0. We reserved permanent URLs for this ontology, from which you can either access the full ontology with all modules imported, or access a specific module. The development of this ontology is maintained via GitHub. This ontology is a domain ontology. First, I will briefly introduce some fundamental domain knowledge needed for a basic understanding of the domain. Essentially, materials design is about designing a material with specific materials properties. Such properties may refer to, for instance, toxicity or strength of the material. Traditionally, researchers research materials properties based on experiments in a lab. However, for some extreme conditions, such as ultra-high temperature and ultra-high pressure, experiments cannot easily be conducted. Therefore, many computer programs or computational methods have been designed to simulate such conditions, and they have broad uses nowadays. Materials calculations run such computer programs to simulate materials properties. Many different software programs can do materials calculations and provide reliable materials data. At the same time, quite a lot of platforms and databases have emerged in the recent decades. The researchers can not only upload their materials data to these platforms or databases, but they can also get the data and use the data in their data-driven workflows. Four well-known databases are shown in this slide. They are Materials Project, OQMD, the Open Quantum Materials Database, AFlow, Automatic Flow for Materials Discovery, and NOMAD, Novel Materials Discovery. In the GitHub link of this ontology, you can find the mappings between these databases schemas and our materials design ontology. While the availability of such databases provides a great help for research in materials design, some problems appear when people need to query data from different databases. For instance, if a person wants to search for a material with the composition gallium nitride in different databases, the result will contain 5 entries from Materials Project and 8 from OQMD. As we can see, Materials Project and OQMD return different numbers of fields. Some fields, such as space group, are the same. Some fields represent the same concept but with different names. For instance, N-sets in Materials Project and the number of atoms in OQMD. The person who queries over multiple databases has to understand the different databases schemas. The researchers from the domain have realized this problem that brings challenges in data integration. An ongoing effort in the domain to alleviate this problem is OptiMed, Open Databases Integration for Materials Design, which aims to make materials databases interoperational by developing a common API. This paper was partly inspired by the OptiMed project, and we used some of OptiMed's terminology in the development of our ontology. This work is motivated by the current challenges in the materials science field. As the data-driven techniques are widely used, many research groups and communities develop data-driven workflows and data repositories. Such data repositories or databases usually store data in heterogeneous ways, as shown in the previous slide. Therefore, it is challenging for users to find data and to integrate data from multiple sources. Furthermore, the current solution relies on file-based exchange, which is not guided by an ontology. Nowadays, the materials science field has a clear interest in making data fair, namely findable, accessible, interoperable, and reusable. And recently, there is a large interest in semantic technologies. However, currently, ontologies related to materials science do not cover the knowledge of materials design. Therefore, we started to build this materials design ontology to cover domain knowledge and to enable the use of semantic technologies in the domain, such as semantic queries and integrated queries over multiple materials databases. The development of MDO follows some relevant scenarios from the NEON methodology, such as the requirement analysis and the reuse concepts from existing ontologies. I will discuss use cases and competition questions in the next two slides. MDO reuses concepts from some good practices in other ontologies, such as the provenance ontology and the unit-related ontology (QUDT). In addition, we looked at some domain ontologies related to physics and chemistry. For example, chemical entities of biological interest and the European materials modeling ontology. We designed the ontology in different modules that allow for easy extendability. During the development of MDO, we discussed with a domain expert to decide the concepts, relationships, and axioms that MDO should cover. We set up the use cases at the very beginning of the discussion with the domain expert. This ontology should essentially represent the knowledge in basic materials science, including materials calculations. As a result, such domain knowledge of materials calculations can be used for standardizing the publication of materials calculation data. This ontology should also have the capability to increase the interoperability among different heterogeneous databases in the field. Further, the ontology should be usable to enrich optimized search functionality. Further, we set up the competition questions that MDO should help answering. We distinguished the competition questions in two directions. We identified general questions that current materials databases can answer. For instance, what's the chemical formula of a structure, and which software produced the results of a calculation. We also identified some competition questions which current materials databases cannot answer explicitly. For instance, what are the input and output structures of a materials calculation? And for a series of materials calculations, what are the compositions of materials with a specific range of a property, for example, band gap? The data that is needed to answer these queries is actually available in the databases, but can also be used if they are encoded with semantics or integrated. Current databases APIs or query mechanisms cannot support such semantic queries or integrated queries. As a result, users cannot get the result explicitly. This figure shows the concepts and relationships of MDO. There are 4 different modules in the ontology, each represented in its own color. In the middle of the figure is the core module, representing concepts such as structure and property and their relationship, for example. The other modules reuse the concepts in the core module. These other modules deal with the structure of materials, with concepts related to calculations, and with provenance information. This figure shows our vision for the use of MDO for semantic search over optimized and materials databases. By generating mappings between MDO and the schemas of materials databases, we can create MDO-enabled query interfaces. The querying can occur, for instance, via MDO-based query expansion, MDO-based mediation, or through MDO-enabled data warehouses. As a proof of concept, we created mappings between MDO and the schemas of some well-known databases. We used the tool SparkleGenerate to define the mappings. Using the mappings, we created a RDF dataset with 85 stable materials from a publication. These 85 stable materials calculation data were also published in the materials project. Further, we built a Sparkle query application that can be used to query this RDF dataset using MDO terminology. An example query is, what are the materials of which the value of the band gap is higher than 5 electron volt? This figure shows how the Sparkle query looks like, and this table shows the result. Basically, what we have done in this work is to provide a domain ontology for the materials design field. We provide the mappings between this ontology and different databases schemas. By using such mappings, we can enable some semantic queries from materials databases. In addition, this ontology is open source. It's publicly accessible via a GitHub project. For the future, in this ontology, we plan to model complex workflows containing multiple calculations. We also plan to build an ontology-based data access application over multiple databases in the materials design domain. Thanks for your attention.